Welcome back. We're going to extend what we know about exponents and logarithms. We're going to work with some equations this time, as well as some applications. You've learned a lot of properties, but not too many, I hope. Remember, exponents or logarithms, that'll get you through a lot. Let's go. All right, properties of logarithms. Just as a bit of a reminder, we have some things we have to consider first. The argument, or the number that's given to the logarithm, has to be positive. The y has to be positive, so we can talk about this. And the a, the base, is greater than 0. And of course, a is not equal to 1 because that's a trivial situation. Now what this says is, if you have two positive numbers that are the same, then their logarithms to the same base will be the same. And vice versa. If you have two logarithms that are the same, then the arguments must have been the same. So this can be pretty handy. Let's take a look at this one. And let's get to the point where you're going to use your calculator. And there's sometimes more than one way to do this, as long as you're handling it with legal moves. So 7x equals 12. Okay, the x is stuck up here as the exponent. So let's take the log. The log of the left-hand side and the log of the right-hand side. Notice I'm using common logarithms. I could have used almost anything, but they are common, so we'll use them. Now, what do we get from this? Well, we can bring this x out front, remember? The exponents can be brought out front of the logarithm. So we'll have x log 7 equals log 12. And we're solving for x, so we'll just divide both sides by log 7. And we've got x equals log 12 over log 7. And then you hit the calculator, which we'll see the result of in a few seconds, because we're going to let the slide review this for you using logs. Okay, getting the solution. Start with writing it down correctly. Take the logarithm on both sides, and they use the natural logarithm. That's fine. This will work just as well. Then, what do? Use the power property to bring x out front, what I call out front. Then divide by natural log of 7, and this is how you're going to calculate what x is. Make sure that you don't write log 12, sorry about that, over log 7. Do not write this as natural logarithm of 12 over 7. No, those are not the same. And here we get the answer. I hope you tried it yourself. Also, you need some practice making these fractions that have natural logarithms on the top and on the bottom, or some combination thereof. So there's our solution set. And there's the comment that I just made. Those two are not the same. Now, how do we get this one? Okay. First of all, make sure you write it down correctly. Check. Second, take the natural logarithm of both sides. And typically, it might be easier to use the natural logarithm most times. You can use the other logarithms sometimes, most times. Just make sure that you don't use a logarithm that has a base that you really don't want to use. We're not going to use logarithm of base 3 or 0.4. That would be real strange. Okay, so what did we do in the last one? We brought this 2x minus 1 out front, and we'll bring this x plus 2 out front, like this. And then, remember, we want the x's, so we'll distribute that. That way we can isolate the x terms. So we just distribute that natural logarithm of 3 over the 1 and the 2x, and over here natural logarithm of 0.4 times the 2 and times the x. That gives us an x term here, an x term over here. We'll get those to both the same side, which we have right here. See the x term here, the x term here. The next thing to do is factor that so we can get x by itself, at least to a degree. So we've got this, and then remember that this is just one number. It's the same thing as if we had 7x. We'd divide both sides by 7. Well, in this case, we divide by something a little bit more interesting, shall we say. And there's our x. All we need to do now is use our calculator very carefully and see what that is. By the way, another thing you should not do is cancel those 2's. 2 is not a factor of the numerator. 2 is not a factor of the denominator. So you cannot do that. If it were like, if you can watch me, if it were like this and like this, then you can cancel the 2's. And I want to clear that out for you. Erase the ink. There we go. Now, we change that back and bring those 2's back to the exponent side. And we've got the expression down here. It's about time to use the calculator, isn't it? So we can simplify that. I'm not sure that we really need to do that, but you could do it if you wanted to. That gets rid of the exponents. It might make it a little bit simpler. It's all up to you. Now remember, these are the exact numbers. So this is approximate because when your calculator is calculating or determining the natural logarithm of 0.48, it has to round off. It doesn't have an infinite number of places. So it gives you an approximation. This bottom expression gives you an approximation. So this is an approximation as well. Although we usually write it x equals just because it's easier. So there's our solution. Next, let's look at this one for a sec. This should suggest to you right away that since we've got this expression, we wouldn't want to use in the common log, we'd want to use the natural log because it has a base of e. So we'll take the natural logarithm of both sides. That'll help us to get the x squared, and we'll be on our way. So we've copied it correctly. Excuse me. Take the natural logarithm of both sides. Very simple, nothing to actually do except write it in. Now, natural logarithm and e to a power are inverse operations. So these two cancel each other out. But that's not the only way of doing it. You could also take that x squared and bring it out front. And I'll show you up here, e to the x squared. And the x squared can be brought out front, so we have x squared natural logarithm of e. Now, what does the natural logarithm of e mean? Well, natural logarithm itself means what exponent we need to get this result. Well, that's almost too simple to understand. It's just 1. So the whole thing is just x squared. Very handy. So here you go. X squared equals the natural logarithm of 200. What do you do then? Use the square root property. Remember, we're going to get two solutions. Plus or minus the square root of natural logarithm of 200. And you can use your calculator to do that. All right, good so far? There's our solution set. Next, since you've done that okay, let's take a look at this one. Of course, since we see e as a base, we're going to instantly go to the natural logarithm. We'll take the natural logarithm of both sides. So copy it correctly, don't make a mistake there. Now, all we've done is use the property of exponents. We're multiplying these two values. They have the same base. Just add the exponents. And that makes it pretty easy. On the other side, we have 3e. Looks good. Now what? Okay. What we can do is we're dividing e into both sides. Okay, how do you get that? Well, let's take a look at this real quickly. We have e to the minus 2x plus 1 on the left-hand side. We're going to divide that by e. Now, what does that mean? You got e to the minus 2x plus 1 over e to the 1. Did you miss that? So, since we're dividing, we'll subtract the exponents, and this is what we get. On the other side, 3e divided by e, of course, is 3. Now what? Take the natural logarithm of both sides. On the left-hand side, the natural logarithm of e and e to the power are inverse operations. So we'll get a minus 2x on this side, and we just have the natural logarithm of 3 there. Or, remember, there's sometimes more than one way to do it. Bring that minus 2x out front. And also remember, the natural logarithm of e is 1. So that becomes minus 2x equals natural logarithm of 3. And just divide both sides by a negative 2. And there's your exact answer. But you want it to the nearest thousandth. So hit the calculator and round off. There's your answer. And if you're looking for a solution set, there you go. Next, let's get something a little bit more interesting, perhaps, or challenging. The important thing about this one is you're going to need one extra thing in your head to get this. You have to be able to notice that, first of all, remember, we've got a base of e. This e to the 2x and this e to the x. This one is the square of that one. So the first thing we're going to do is we're going to let, I'm going to use y, but you could use anything. I think they maybe use u. Let's see if I remember. Let u be e to the x. Then the first one becomes u squared minus 4u plus 3 equals 0. You should be able to factor that in short order. U minus 3, u minus 1. That gives you two solutions. Two in-between solutions. U equals 3, u equals 1. But u is e to the x. So what we really have is e to the x equals 3 and e to the x equals 1. The one on the right, if you're thinking quickly, you notice anything to the 0 power is 1. So you can do that real fast. Otherwise, you can take the natural logarithm of this, natural logarithm of this, and you get the same result. So x equals 0 is one solution. Over here, we can do the same thing as I did secondarily there. Take the natural logarithm of both. E to the x equals the natural logarithm of 3. Bring that x out front. Equals natural logarithm of 3. Natural logarithm of e is 1. So it's just x equals natural logarithm of 3. Grab your calculator. If you want the exact value, you're finished, really, because the exact value is this. Your calculator will only give you an approximate answer. So keep an eye on what you're looking for. You want the exact answer, that's the end of the line. And of course, x equals 0 is exact. And here's another way of doing it. A little bit more complicated perhaps, but you could do it that way. Replacing they use the u as well. So this should look familiar. There's the factor, the two intermediate results. We'll substitute back in and solve both of those equations, and you get your two exact solutions. And if you're looking for a solution set, which you did not ask for, but writing it like this is perfectly fine. Oops, there we go. Next, let's look at this one. In this one, x is sort of trapped inside the natural logarithm function. How can we get it out? Well, you might guess we would take, first of all, we can divide both sides by 7. Did you catch that? If you did, good. Now what do we have? Natural logarithm of x equals 4. Take e as the base of each one. These two cancel each other out because they're inverses. You get just the x. If you want the exact value, there you go. Now if you're trying to figure out how long your house is going to be, you need an approximation. There's your exact answer. Solution set notation, there you go. Next, we're using a different base this time, just to give you a little bit more well-rounded approach to logarithms and exponents. Let's see how this goes. You know that you're going to use the base of 2, and make sure you write it down correctly. Now, in exponential form, remember, when you do that, on the left, for example, Well, don't need the left. You always start with the base. The base in this case is a 2. What's the exponent? Well, logarithms are exponents, so there's the exponent, 3. And what's that equal to? Well, the only thing that's left is x cubed minus 19. Solve for the x cubed first, and then take the cube root of both sides. We don't have to worry about plus or minus because this is an odd power, so we don't need the plus or minus here. Just leave this sign here the same as this sign here. In this case, positive. And there's our solution set, 3. A good experiment actually for you would be to take this 3 and check it by doing this on your calculator. See if you can do it. It can be pretty easy if you know where to go. Or there are some tricks too, of course. If you can do this with your calculator, you're in good shape with logarithms, that's for sure. Next, we have a logarithm equation here. All of these are logs. They're common logs because you don't see a base here, so it's automatically a 10. The good thing is these logarithms have the same base, and we can get the exact values like this. Keeping in mind, of course, this almost gives something away, but let's keep on going. So here's our original. Copy it correctly. Now, one thing, you're subtracting logs. That means you're subtracting exponents. That means you're dividing these arguments, x plus 6 and x plus 2. There's our property of quotients. And notice we've got 2 logs that are the same. That means the arguments must be the same. We had that property earlier in these slides. So we've got this, and we can solve for x. Multiplying both sides by x plus 2. And then we've got a quadratic on our hands, so we'll have to solve this to get 0 on one side. There we go. This is pretty easily factored. And then we've got 2 solutions because we'll set each of those factors equal to 0. You get -3 and you get a 2. Now remember, you always should check to make sure that the numbers you get, which look perfectly fine, actually work. The trouble is, if I put this -3 in here, what do I have? I have the log of -1. Can't do that. No logs of negative numbers, or 0 for that matter. It has to be positive. This number has to be positive, not the x. The x plus 2 and the x plus 6 must be positive. Check the 2. The 2 will be okay as a number in here. That'll give us 8. 2 in here will give us 4. And of course, over here as well, 2 over there. So our solution set doesn't have 2 values. It only has 1 solution. Next. That's pretty much what I said, right? The domain, or the x's you're allowed to use, are only above 0. Excuse me. All right, this looks a little bit complicated, but really not too much. So remember what we did before? First of all, make sure your copy is correct. Next, since you're taking each side and using that as an exponent, and this is what you get. Now the log of base 2 and the exponent of 2 are going to be inverses. So all you get is what's inside. And on the right hand side, 2 cubed, we know what that is. It's 8. Bring everything to one side because we do have a quadratic. And we can try to factor that thing. Now if you have some trouble, that's quite possible. You could always use the quadratic formula on this one. It might be faster. Or you could use what I've told you is the AC method. And that works. I've done it. I tried these myself. Now, once you have these factored, set each one equal to 0. Zero factor property. Solve for x. And you got 2 possible x's. But we have to check them out, remember? However, it does work. The first one leads to 8. Second one leads to 8. And that is definitely true. This says the exponent of 2 will have to be a 3 to give you the 8. Next, we want the exact values. Remember, no approximations here. Now we're adding these, so that means we're multiplying the arguments. So we have this, and since we had just logarithms, it's automatically base 10. It's common logarithms. Now we'll use both this and this as exponents of what? 10, of course. So 10 to this power and 10 to this power. Excuse me. Of course, these two are inverse operations, so you end up with what's inside. And on the other side, 10 to the first power, 10 of course. Move everything to one side to solve that quadratic. Now this time, factoring didn't work. So this is why you really need the quadratic formula in your head. Looking it up, even if you've got a take-home test, looking it up wastes a lot of time. So evaluate that. We get 2 proposed solution or possible solutions. Now if you look at this first one, 1 minus the square root of 145, well, the square root of 144, for example, is 12. So on the top we'd have something similar to 1 minus 12. That's negative. Divide by 6, it's still negative. So you can't use that for x. However, this positive value will work. Of course, you ought to check it too. So you're going to reject this one. And keep the second one. Make sure you're checking it though. If you need a quick way to check that, check with me, but I think I mentioned it already, but I don't mind answering again. So another way we could have done this is we could have changed it like this, making this the right-hand side into a logarithm, because 1 is the power of 10 that will give you 10. If you can think of that, then since the logs are the same, the bases are the same, then the arguments are the same as well. And you go on from there, getting your quadratic, 0, and the zero factor property, and checking the two proposed solutions. Next one. We're working with natural logarithms, and this one right here, I hope you can figure that out. Now it can look a little bit complicated, but it really isn't, because you've got the natural logarithm of e to a power, so the answer is just the power itself. Did you get that? Anyway, so this is the first one, the one I just mentioned. The natural logarithm of x is what you get out of this, because these are inverse operations. The second part stays the same, third part stays the same for now. So, natural logarithm of those two, we're subtracting exponents. Logarithms are exponents, so we're dividing, and we have that natural logarithm on both sides. Now we'll take e to that power, or the inverse, and we have x over x minus 3 equals 2, and that's pretty easy to solve, right? Multiply both sides by that denominator. Quick check, and make sure the 6 works, of course. 6 will work in here because it's a positive number. 6 will work in here because that makes x minus 3 positive as well. We're in good shape. There's our solution set. So here are some things we've actually been doing. If you want to solve these exponential or logarithmic equations, remember, the arguments have to be positive, not 1. They have to be real numbers. If you've got this, a to the sum function equals b, then you can take the logarithms of both sides, using, of course, the base a, because that would definitely be the easiest way. So logarithm of the first side, logarithm of to the base a of a to a power is just the argument itself, f of x. And on the other side, just b. So you can change it to exponential format. A is the base. Remember, it always starts with a base. A to b power equals f of x. There you go. And then you've got an equation, and it's equivalent to, if you take the logarithm of this side as well as that side, this equation is equivalent to this one. And one like this looks a little bit familiar, right? You might have to solve for f of x first, and then solve the equation, and then, of course, when you're finished, check that the possible solutions actually are in the domain. Can you really use them? Now here's an example that you might find interesting. It's the strength of a habit, like habit of going to school every day, habit of having the same thing for breakfast every day. There are lots of habits, of course. Well, the strength of that habit is following this equation, or this formula, according to C.L. Hall. Now, I'm not a psychologist, so I'm not familiar with C.L. Hall, but we can solve that equation for k. That looks a little bit daunting, doesn't it? But one piece at a time. First of all, copy it correctly. We'll divide by 1,000. We're getting closer to that k. Now we can subtract the 1 from both sides. We're getting closer to the k. And then what? Notice that over here, this is a minus e to the minus kn. That's not a good sign. We don't want that minus sign. How can we get rid of it? Take the opposite of both sides, or take the negative of both sides. And there you go. It changes the sign of all the leading pluses or minuses. Now we've got e to a power, and of course we're going to take the natural logarithm of both sides. Natural logarithm and e to a power, you just have the power. So that's pretty easy. And the right hand side, just leave it the way it is. Don't bother with it. Now what do? You want to find out what k is. So we'll do what? Divide by negative n, or multiply by negative 1 over n. Either way, it's the same operation. And there you found k. This is your k. But of course, someone has to tell you what the n is and what the h is. Then you'll know what your friend k is. So if we can find one pair of values of h and n, we'll have k in our back pocket. Now here's an example of video content. And this one I think you'll find pretty nice. First of all, read this carefully. The x is going to represent, or the t rather, the t is going to represent the number of years after 2012. Now, what does that mean? That means this is 1 year after 2012, this is 2, this is 3, and so on. And then these are the number of viewers in millions. Here is our model. Our model says if you want the number of viewers, here's how you do it. Take 23.19 times the natural logarithm of whatever t is at that particular time, add 75.19, and you'll get the number that's over here, or pretty close to it, if this is a good model. So, how many viewers did we have in 2019? Well, remember what t is? T is the number of years after 2012. So t equals 7. So all we need to do is put 7 in where these t's show up. A little bit of calculator work, unless for some reason you would want the exact amount. But for this, I don't think you would, because you want an approximate or an estimate of how many viewers. And remember, this is in millions. I guess that didn't turn out too well, did it? There we go. And of course, that refers to the year 2019. What if we take it the other way? When will we get to, maybe this is some kind of magic number for us. When we get to 130 million, something special happens perhaps. So how can we find the year that we get to 130 million? Well, that means f of t is 130. Solve for t. So the 130, this is our f of t right here. Here's the rest of the formula. All we have to do is solve for t. Subtract the 75.19, divide by the 23.19, And we've got the natural logarithm of t, not t, but we know how to do that now. We'll take e to that power and e to this rather large exponent, and we'll have t. T equals this rather large exponent temporarily. Our calculator can handle that now. One thing you don't want to do, big hint, the 54.81 divided by 23.19. Don't divide that and round it off, because that will change this number. Leave these numbers the way they are, or keep all the decimal places for the result for that, and then use that for the exponent of e. So we've got 10.63, that's the number of years after 2012, remember. And that tells us that based on that model, if the model's good, that will reach 130 million in 2022. All right, folks, that's it for this time. Let's take a look at what we'll be doing next time. We'll be doing a little bit of modeling. We'll have some interesting examples, I think, for you. Until that time, you take care and we'll see you.